Okay, so we were studying how to evaluate a property of moist air. So moist air is a mixture of dry air and water vapor. So when we say moist air, it's a mixture of dry air and water vapor. So we can use the ideal gas equation to evaluate their properties. So it's going to be PV. PV is nRT. PV is N. PV is nRT. So in this case, we have two components in the mixture. So if you want to apply this ideal gas equation for this dry air, you can say PA times V is NA times RT. So this one is a partial pressure, which you can determine by the mole fraction of dry air times the mixture pressure. And this mole fraction can be determined by the number of moles of dry air divided by the total number of moles of the mixture. So this N is Na plus Nv. So this one is water vapor. And this one is dry air. So that's how we determine the partial pressure of dry air. And this is the number of moles of dry air. And the rest, volume, the gas constant R, and the mixture temperature T, we use the same value. On the other hand, if we want to use this water vapor, then it's going to be PV times volume is the number of moles of water vapor times gas constant times temperature T. So in this case, this is the partial pressure of water vapor, so which can be determined by the mole fraction Y of water vapor times the mixture pressure. And this mole fraction can be determined by the number of moles of water vapor over the total number of moles, which is Na plus Nv. And this one is the number of water vapor. So that's how we apply the ideal gas equation on a molar basis for dry air and water vapor. Since it is a mixture of dry air and water vapor, the ratio between dry air and water vapor is going to be the key to analyze the properties of this water vapor. Then then can we have what is the maximum amount of water vapor can be present in dry air? We can determine the amount of water vapor by using this TV diagram. So let's assume that, that we are talking about, we are investigating the moist air in this classroom. Then the temperature is going to be 20 degrees Celsius, depending on the amount of water vapor. The water vapor can be anywhere on this line, okay? Not beyond this point. So from here to the right. And this point is when the air in this classroom has the maximum amount of water vapor, that is saturated vapor. So at this point, the relative humidity, which is high relative humidity of moist air, is going to be 100%. If you have more amount of water at this temperature, then only up to this point, water is going to present in the air. The excess amount is going to be condensate and then becomes liquid water, okay? And if we decrease the water vapor, the amount of water vapor, this one moves to the right, and the relative humidity decreases when we go in this direction, okay? Then let's say the amount of water vapor is this point. Let's assume that the amount of water vapor in this classroom presently is going to be this point. So current position. So this is the current position. So this is the water amount. Then if you increase the water amount by using a humidifier, then water vapor moves to the left-hand side until it hits this saturation curve. If you use a dehumidifier, then we are decreasing the amount of water in this air, then it moves to the right-hand side. If you decrease the temperature of this classroom without changing the amount of water, then partial pressure. By the way, how do we determine this partial pressure? The partial pressure PV can be determined by the number of the mole fraction. The amount of water, the mole fraction give you the amount of water in the mixture times the pressure. So as long as, so this one can be determined by the mole fraction, the ratio of water vapor times the pressure of the mixture. So if you decrease the temperature or increase the temperature of the air in this classroom without changing the amount of water vapor, then this PV does not change because the pressure in this classroom is constant. If we heat this air, if we heat the air in this classroom, its temperature goes up. However, the pressure in this classroom does not change, right? And if we don't add or remove water in this air, then the mole fraction stays the same. So as long as you have the constant temperature and constant pressure, when you increase or decrease, the water vapor in this classroom is going to move this way if you increase the temperature, or this way if you decrease the temperature. So this way, if you increase temperature this way, if you decrease temperature. Or if you increase, if you add water, then move to the left. If you decrease water amount, move to the right. If you increase temperature this way, if you decrease temperature this way. In winter, when you are driving, sometimes that, the windshield is going to be foggy, so you cannot see front. Why is that? This is the cabin temperature. This is the temperature of the air in the cabin. However, the windshield is going to be at lower temperature than the air in the cabin because the outside is cold, right? So the air near the windshield is going to be at lower temperature than 20 degrees Celsius. What about the windshield is sub-zero, somewhere down here? Then, since you do not remove or add water vapor within the cabin, it's going to move up or down since the temperature near the windshield of your car is lower than the temperature of the air in the cabin. Water vapor temperature goes down, and once it hits this point, what is this point? Saturation curve. What is the relative humidity at this point? 100%. So if you decrease the temperature, then what happens? You have liquid water. And the liquid water molecules on the surface of windshield, that's what you see, the foggy windshield, is the result of condensation of water at 100%. So to remove that, to remove that foggy windshield, how do you do that? You need to turn on the air conditioning to remove water, and you need to turn on the heater to increase temperature. So to get away from this point, that's how you, clear the windshield. That's what happens, when you drive, on a winter day, and then if you see a foggy, the windshield, then means that, the water vapor near the windshield is at this location. So if it goes further this way, then means that you cannot see anything. So you need to move up by increasing temperature, or to the right by decreasing the amount of water. And can you increase the temperature of the, near the windshield? If you turn the heater on without changing the amount of water, the temperature of the air in the cabin is going to increase. However, the temperature near the windshield is going to be still at low temperature because outside is cold. So turning the, the heater on does not help a lot, but you need to turn on the air conditioner so that you can remove the amount of water. Because, the in air conditioning, the system, it removes the water. That's what you can study later, when we, talk about dehumidifier using air conditioning system later in this chapter, okay? So this is how, the moist, the water vapor behaves in moist air. And then, let's learn, how to analyze this water vapor thermodynamically. So first, we need to understand, the ratio between dry air and water vapor. The first parameter, the first property that we use to, to determine the ratio between dry air and water vapor is this phi, relative humidity. So this phi is what we use a lot in our real life. So this one gives, that has a value between 0 and 100. 0% means that there is no water vapor. You only have a dry air. if you don't have any water vapor, what is the mole fraction of water vapor? 0, because you don't have any water vapor. So if the mole fraction of water vapor is 0, then the partial pressure of water vapor PV is 0. So this relative humidity is going to be 0. By the way, the definition of the mathematical form of relative humidity is going to be PV, the partial pressure of water vapor, and PG. PG is nothing new. This is the saturation pressure, P set. So if you want to have the maximum amount of water vapor present in moist air can occur when water vapor is on this saturation curve. And what is the pressure? PV on this saturation curve. Going to be saturation pressure. So PG is when I is 100%. That is P set. And the PV, the partial pressure, we are going to compare the partial pressure of water vapor and the maximum partial pressure possible, which is P set. That's how we determine the relative humidity. So relative humidity, the 100% relative humidity occurs when the partial pressure of water vapor is going to be the saturation pressure. And if you go to the steam table, you can find the saturation temperature. If the partial pressure of water vapor is the saturation pressure, that's when you have the maximum amount of water in moist air. So if you add any more water molecule, either in the form of vapor or liquid, it cannot be a vapor anymore. It's going to condensate and it becomes liquid. That's how we remove water by using air conditioning system. Sometimes, if you go to the basement or somewhere, where your air handler is, you see water comes out, right? That water is condensation because the pressure inside the air handler is going to be the saturation pressure. Then water is removed. And then in the fresh air with decreased amount of water vapor goes into the house, right? That's how we remove water. That's how the dehumidifier works. So we use this relative humidity a lot in our real life. If you, go check the weather, you can find the relative humidity. But this is not the ratio of dry air and water vapor that we use in our thermodynamic calculation. Instead of this relative humidity, we use humidity ratio, omega. So humidity ratio, omega, is the one that we use in our energy balance equation, entropy balance equation. So what you need to know is how to convert between the unit that we use in our real life and the parameter that we use in our thermodynamic calculations. So there are two of them. Relative humidity, that's what we use in our real life. And the humidity ratio, this is what we use in our thermodynamic calculation. Okay? So we are going to study how to convert between relative humidity and humidity ratio first. Then we are going to study how we add this omega in our energy balance equation that we studied in Thermodynamics 1. That's what we are going to do. And after that, that's all, then we can study, the energy balance equation or entropy balance equation for, the various engineering systems. So we are going to study two systems. One is mixing chamber and the other one is dehumidifier. So mixing chambers, we have two inlets, and dehumidifier, we have two exits. Okay, So let's talk about how to convert between relative humidity and humidity ratio. Of course, we can use this equation. The partial pressure of water vapor. So PV is the one that we are going to use to convert between relative humidity and humidity ratio. Yes. Okay, okay. I will do that here. So relative humidity that we use in our real life can be determined by PV, not pressure times volume. This is the partial pressure of water vapor divided by PG, which is the partial pressure of water vapor when the relative humidity is 100%. In other words, T set, saturation temperature. And this PV can be determined by the mole fraction Y of water vapor times the mixture pressure, which is the pressure of moist air. So this is what we use in our real life. Then what about the one that we use in thermodynamics, humidity ratio? This humidity ratio is omega, it's not W, mass of water vapor divided by mass of dry air. So this V and A, they are subscripts. So mass of water vapor, mass of dry air. When I say subscript A, that means dry air. And V means water vapor. Then this omega can be determined by this equation. Omega is 0.622 PV, the partial pressure of water vapor, divided by P, the mixture pressure, minus PV. And the way that we got this equation is pretty simple. We use the ideal gas equations for water vapor and the dry air. That's how we got this equation. This one? This is a process. This is how we got this equation. So you don't need it as long as you wrote this down on your formula sheet. If you don't remember, this is how you get. So you apply PV nRT for water vapor. PV nRT. The ratio is going to be the humidity ratio. Since we know temperature is the same, gas constant is the same, volume is the same, and the only differences are molecular weight and the partial pressures. So that's how we got this 0.622. This is actually the ratio in molecular weight. Okay? Finding this equation is pretty simple if you just follow, but you don't have to. As long as you know this one and relative humidity. So you only need 3 equations. So relative humidity phi, and the definition of humidity ratio, and how you get this humidity ratio by partial pressure. Because this partial pressure is the one that connects relative humidity and humidity ratio. Then, if I have the relative humidity, then you can determine the humidity ratio. If you have humidity ratio, you can determine the relative humidity. Let's practice. So let's say the temperature of this classroom is T is 20 degrees Celsius. And let's pick any relative humidity. 50%? Sounds right, okay. So relative humidity is 50%. Then please determine humidity ratio. So if this is the problem, first, the most important parameters here is going to be PV. So we are going to determine PV, the partial pressure of water vapor. How do we do that? We know relative humidity phi, so phi is by the definition PV over PG. Then what is PG? Saturation pressure. Saturation pressure at what condition? At 20 degrees Celsius. Then you can go to the steam table to determine P set at 20 degrees Celsius. So which table do we have to use to determine P set at 20? Since you know 20, what is this 20? Temperature. So you go to the temperature table. So let's go to the temperature table, table A2, and find 20 degrees Celsius. So here it is. At 20 degrees Celsius, the partial pressure of water, the saturation pressure is going to be 0.0234. 0.0234. So this one from table A1, I'm sorry, A2, 0.0234. What is the unit? The unit in the steam table is going to be bar. Oh, by the way, in Thermodynamics 1, we used kilopascal more often. But when we talk about moist air, the people whoever in the field like to use bar more often. So I will do the same, so you don't get confused when you go to the field. So let's use bar. And the relative humidity is 50%. So this one is 0.5. Then you can determine the partial pressure of water vapor. So the partial pressure of water vapor from this calculation, PV is going to be 0.0117. 117 bar. Then, how do we determine the relative humidity? This one. I'm sorry, humidity ratio. Omega can be determined by 0.622 PV over P minus PV. So in this case, PV is 0.0117. What is the pressure inside this classroom? Approximately 1 bar, right? 100 kilopascal. So 1 minus 0.0117. That's how you determine the relative humidity. Calculator. So one bar means 100 kilopascal. That is the pressure of the mixture. So moist air. So 1 bar is the pressure of the mixture, which is dry air and water vapor. And when we calculated the partial pressure of water vapor only, that was this number. Then, what is the partial pressure of dry air? What is the partial pressure of dry air? This one. So the moist air has 2 components, vapor and air. So the sum of all the partial pressures should be the mixture pressure. So the partial pressure of dry air should be 1 minus this number, 0.0 9, 8, 8, 3 bar. So that is going to be the dry air, the partial pressure of dry air. Yes. Okay. So if you calculate the sum of partial pressures of each component in the mixture, this one is 2, but if you have, the 10 different components, if you calculate the sum of them, it will be the mixture pressure 1. Oh, by the way, if you do the calculation, the relative humidity is 0.0117 divided by 1 minus 0.0117 and multiply by 0.622, we get 0.00736. What is the unit of this humidity ratio? None. There is no unit. It is mass divided by mass, kilogram divided by kilogram. So the humidity ratio omega has no unit. And usually, our assumption, if you remember the first slide of this lecture, of this, the moist air, our assumption is that the mass of water vapor is extremely small compared to the mass of dry air. So omega, humidity ratio is mv over ma. So usually humidity ratio should be very small number because the mass of water vapor is very small compared to the mass of dry air. So usually 0.00 something. If you get large number, that means that made a mistake. Okay? So that's how you convert between relative humidity and humidity ratio. The key parameter is going to be PV. So as long as you have PV, then you can determine the relative humidity and humidity ratio. Any question? So this P is the mixture pressure, total pressure. And total pressure is the sum of every partial pressure in the system. So how many partial pressures in the system? 2. The one with dry air, the other one with water vapor. So if you calculate the sum of these two, it should be 1 bar, which is 100 kilopascal. So that's everything about, how we quantify the ratio between dry air and water vapor. Now let's talk about, how we can determine the mixture properties. If you want to calculate, one of the most widely used thermodynamic properties is enthalpy, or internal energy, or entropy. And then the way to determine the mixture enthalpy, which is the total enthalpy, is going to be the enthalpy of dry air plus the enthalpy of water vapor. So the total enthalpy H can be determined by the enthalpy of dry air plus the enthalpy of water vapor. You cannot calculate the total enthalpy directly because there are many different mixtures. 1% water, 99% dry air, or 2% water, 98% dry air. So you need to calculate the enthalpy of each component separately, independently, then calculate the sum of them. That's how we get the mixture enthalpy. Then these H, the capital H, is an extensive property. So we want to use specific property in our calculation. So this capital H can be determined by lowercase mass times lowercase h. So instead of this capital H, we can say mass of dry air times specific enthalpy of dry air plus the second one, mass of water vapor times the specific enthalpy of water vapor. So that's how we determine the mixture enthalpy. But still, this is not an intensive property. It is already multiplied by mass. But you remember when we studied energy balance equations in Thermodynamics 1, we used intensive properties such as lowercase h, lowercase u, and etc. So let's get mass out of it. So between these two, what is the majority mass? Mass of dry air. So you can take this one out. You can say mass of dry air times specific enthalpy of dry air. Then we have mass of water vapor divided by mass of dry air times the specific enthalpy of water vapor. Then there's one thing that you may remember, this one, mv over ma. What is it? That is the definition of humidity ratio. mv over ma is the definition of omega, humidity ratio. So we can replace this one with the humidity ratio. So H, the total enthalpy of a mixture, can be determined by Ma, the mass of dry air, times HA plus this one, omega, times HV. Then how do we determine each specific enthalpy? It's simple. Previously, this H is for a mixture. So we cannot directly, determine the mixture property. But if you separate into two, then now you can determine this lowercase h, because this one is dry air only. So we can use ideal gas air property. So there is a table, and this one for superheated vapor, phase change process number 5. So that's how we can evaluate each H. And if you already calculated the humidity ratio, you can determine the total enthalpy. And this total enthalpy is going to be the one that you use in your energy balance equation. Sometimes, when the humidity ratio is high, then we can approximate HV by Hg. And do you remember what is Hg? H is a specific enthalpy. What was, what was this G? Phase change process number 4, saturated vapor. So that's one of the ways to determine HV, which is right here. So that's everything about the theory behind, the moist air. And we are going to solve as many problems as we can in the classroom, so you can learn how to use those energy balance equations and entropy balance equations that you already studied in EGR456. Okay, this time we are going to use the mixture. Any question up to here? No? Okay. Air enters a compressor operating at steady state at 50 degrees Celsius, 0.9 bar, 70% relative humidity, with a volumetric flow rate of 0.8 cubic meters per second. The moist air exits the compressor at 195 degrees Celsius, 1.5 bar, assuming the compressor is well insulated. So if you assume that the compressor is well insulated, what does it mean? Adiabatic system. That means there is no Q. Then let's write down the energy balance equation. The energy balance equation for compressor can be found, if you don't remember, we can get the energy balance equation by using the general energy balance equation for steady state, steady open system. So what was the general energy balance equation? Q dot in plus W dot in plus M dot at the inlet. So let's say inlet is number 1, and this one has enthalpy H1 plus kinetic energy V1 square over 2 plus potential energy gravity times elevation Z2 Z1 is going to be Q dot out plus W dot out plus M dot at the exit. So let's say exit is number 2. This one has enthalpy, kinetic energy, and potential energy. So, but we are not going to use this equation as is. This is just the general form. So let's simplify this energy balance equation for this compressor, which is adiabatic. So it's an adiabatic compressor. So there's no Q. And it's a compressor. Does it produce work or does it consume work? So compressor consumes work. So there's W in, and it doesn't produce work. And what is the counterpart? What is the one produces work rather than consuming work? Turbine. So there are two things. Turbine produces work. Compressor consumes work. So that's a two separate things. But the energy balance equation looks pretty similar. And you can neglect kinetic energy change and potential energy change. Then how can we, neglect kinetic energy change and potential energy change? It's simple. Unless, your compressor is as tall as Mountain Everest, we don't need to worry about, the potential energy. But what about kinetic energy? The inlet of the compressor, the exit of the compressor, if you have a similar pipe size, then the velocity and cross-sectional area is about the same. So you can neglect, the velocity change between the inlet and the exit. So kinetic energy and potential energy are usually neglected when you have these systems. Then what do we have? W dot in and the rate of enthalpy, the rate of enthalpy at the inlet, the rate of enthalpy at the exit. However, we don't want to use just M dot H because now we have a mixture M dot of A, M dot of V. So let's combine these two. Then what do we get? W dot in, which is this power input, plus H dot 1 is H dot 2. So that's the energy balance equation for this adiabatic compressor. Any question up to here? So there's no new thermodynamics. It's just chapter 4 in EGR456. Now, let's write down the energy balance equation. So how do we determine this H? From here, we learned this H can be determined by this equation. MA times HA plus omega HV. Then I'm going to rewrite that. So this one is M dot in plus M dot of A at the inlet times HA at the inlet plus omega 1 times HV at the inlet is going to be m dot H2. A2 HA2 plus omega 2 omega 2 HV2. I just used this equation here. So the main equation was H is MA times HA plus omega HV. So we use this equation. Then what happens in the compressor? There is only one inlet and one exit. The amount of air should remain constant, right? Can you destroy air? No, we can't. Is there a chemical reaction between water and air? No. So the amount of air should be constant between the inlet and the exit, right? The amount of water vapor should be also constant between the inlet and the air exit. So that means m dot A1 should be the same as m dot A2. So I'm going to remove this subscript 1 and 2. There's only one m dot A. What about omega? Omega is the ratio between the mass of water vapor and the mass of dry air. And since there is only one inlet and one exit, of a compressor, and there is no chemical reaction, nuclear reaction, the mass of water and the mass of dry air should remain constant. So the ratio should remain constant because this one is constant, this one is constant. The ratio is constant. So omega 1 is the same as omega 2. So I'm going to remove omega 1, omega 2. So now we can simplify this equation because we have this one is the same, this one, they're the same. So why don't we move this one to the right-hand side? Then W dot in, that's the power input to the compressor, is going to be m dot of A times HA2 minus HA1 plus omega times HV2 minus HV1. So this is the governing equation. So up to here, thermo 1, and now thermo 2. So I didn't change anything. We are using the same energy balance equation, but when you have a mixture, when you have a moist air, this energy balance equation becomes in this form. So this is the general form of energy balance equation when you have moist air in an adiabatic system with one exit, with one inlet. So I guess that it's time to analyze the system. So let's see, let's evaluate one by one. This power input is the unknown that we want to determine. So B, the power input, this is what we want to determine. Yes. Okay. Then what about this m dot A? Do we know this m dot A? We don't. However, we have information to determine this m dot A. What is that? The volumetric flow rate. So we have the volumetric flow rate, so we can determine m dot A, no problem. What about H2, H1? So this one is not just H. This is H of A. What is A? Dry air. So we want to determine the specific enthalpy change of air between the inlet and the exit. So how do we get that? We can use a table, ideal gas air table, to determine this one and this one. As long as we know the temperatures, and we know the temperatures. The exit temperature is 195, the inlet temperature is 50, so we can determine these two. No problem. What about HV? It also depends on the temperatures. So we have a table for HV as long as we know the temperature, 50 and 195. I'm going to show those tables later. So the only thing that is missing here is going to be this one, humidity ratio. So let's determine this humidity ratio. So how do we determine this humidity ratio? There were two equations. You may remember these two equations. Phi, the relative humidity, is PV over PG, and omega is 0.622 PV over P minus PV. So it looks like we need to determine PV first. So let's do that. So I'm going to write these two equations on the left-hand side for your information. So phi is PV over PG, and omega is 0.622 PV over P minus PV. Then, let's see, what information do we have? We know the temperature, pressure, and relative humidity. So let's analyze the inlet of this compressor. So at the inlet of the compressor, we have T1, which is 0.9 bar, and we have T1, which is, where is it, 50 degrees Celsius. We have relative humidity, phi1, which is 70%. So we can start with this relative humidity. This relative humidity can be determined by this equation, PV over PG. Then what is PG? That's the saturation temperature. So PG is the saturation temperature. T set at what condition? At 50. So let's find P set at 50. Where's my team table? So let's find 50. 0.014567, and where's the 50? The last one is 45. So let's go to the next slide, next page. Oh, there's a 50. What is the pressure, saturation pressure? 0.1234? No, 1235. So 0.1235, that is the T set. 0.1235 bar. Then from here, we can determine PV. What is PV? PV is, this one is 0.7, so we can calculate PV, that is 0.08645 bar. Then once you know PV, can you determine omega? Yes, we can. The omega equation is here. So omega 1 is 0.622 PV1 over P1 minus PV1. And what is PV? We already found PV. This one goes in here. This one goes in here. What is P1? 0.9. So this one is 0.9. And we know PV1 from this relative humidity. So we can calculate omega 1. So from this equation, omega 1, the humidity ratio, is going to be, where is it? I calculated it. 0.066. Then you can say omega 1 is the same as omega 2. You can say omega. Then this one goes there. What about HA2 minus HA1? We can go to table 820. I think it's 820. 821, 820. Oh, there should be 820. No, oh, that's not 820. So we need to find 822. 822. So if you go to table A22, we can find HA at 50 degrees Celsius and HA2 at 195 degrees Celsius. So let's find the value. So what is the inlet temperature? 50. So this one at 50. And what is the exit temperature? 195. 195 degrees Celsius. So where is 50? By the way, the unit in this ideal gas properties of air is going to be in Kelvin. So not 55, you have to find 323. So where is 323? Between these two numbers. So to determine H, we need to do a linear interpolation between these two numbers. And I'm pretty sure that you know how to do a linear interpolation, right? So the number is going to be between these two. So if you do the linear interpolation, we get HA1 323.3 kilojoule per kilogram. What about at 195? 195 is 468. So where is 468? Between these two numbers. So where is H? Between these two numbers. So it's going to be 460 something. And if you do, we get 470.2 kilojoule per kilogram. So that's how you determine HA. What about HV? We can go to another property table, which is table A23. So there's a table A23, but you know, you need to focus on here how to evaluate, you know, the value on this table A23. So let me zoom in. So again, the same thing. We are going to use temperature 50 and temperature 195 degrees Celsius. So 50 is 323 Kelvin. So where is 323 Kelvin? Between these two numbers. So let me zoom in. So 323 is between these two numbers. Why it is moving? So where is water? Water vapor right here. So where is H? This one. So let's go down and between, so the temperature we are looking for is 323 Kelvin, that is 50 degrees Celsius. So we need to do a linear interpolation between these two numbers. But don't you think there's something interesting here, something weird? So if you do a linear interpolation between these two numbers, can you determine the specific enthalpy of water, H? There's something interesting. Something doesn't seem right. Which one is that? What is that? Is that the H that we're looking for? No. What is the problem? That looks H, but not exactly. It's H bar. When do we add bar on top of a property? When it is on a molar basis. Then how you convert that into a mass basis? H bar divided by molecular weight is H. So we can do a linear interpolation between these two numbers, but after that, we need to divide by that capital M. What is that capital M? Molecular weight. Lowercase m is mass, capital M is molecular weight. Then what is the molecular weight of water? You can go to table A1. So molecular weight of water, this one, 18.02. So from here, you can find H bar value at 323 Kelvin and then divide by molecular weight of water, which is 18.02 kilogram per kilomole. So let me show you. It's going to be 10,000, about 700 something. So let me find it for you. 10,740. 10,740. So this one is 10,740. What is the unit of this H bar? Kilojoule per kilomole. Kilojoule per kilomole. And you need to divide by what? The capital M. Molecular weight of water. 18.02 kilogram per kilomole. So what was the table number? 823. Then you can do the same at 195 degrees Celsius from the same table 823. So let me give you the number. It is 15,707 kilojoule per kilomole per 18.02 kilogram per kilomole. So that's how you determine all the properties. I think so. Yeah, it's a caramel. I don't think so. I don't like mocha one. Chocolate flavor, I prefer caramel. Okay, one more thing. So we need to determine the mass flow rate. So can we determine this mass flow rate? We can, because we know the volumetric flow rate. The volumetric flow rate at the inlet is going to be 0.8 cubic meters per second. So V dot is 0.8 cubic meters per second. Then how do you get this mass flow rate? You need to multiply by density. Then where do you get this density? From ideal gas equation. PV is RT. And the inverse of this density is going to be specific volume. So the equation we are going to use is P over rho is RT. But there's one thing that you need to be careful. The temperature T is going to be the inlet temperature, 50 degrees Celsius. But we know we have to use Kelvin. So 50 plus 273. What about gas constant? Gas constant of air is going to be 0.287 kilojoule per kilogram Kelvin. So density is the unknown. What about the pressure? Can we use 0.9 bar for this ideal gas equation to determine the mass flow rate of dry air? You can't. Then what pressure should we use? Not this one, but the partial pressure of dry air. And how do you get the partial pressure of dry air? PA is P minus PV. So 0.9 minus 0.08645. So this PA goes in here. Then you can determine the power required to run this compressor. And the power required is going to be, so where is it? 115.9 kilowatts. So that's how you solve this energy balance equation. This is a very basic problem that you are going to see in your first exam. Yeah. Because this is the easiest one. But you can see there's nothing new. We use the energy balance equation and we convert this energy balance equation to this form because we have a mixture. Then we identify each term one by one, not from an equation, from a table 822, 823. And the unknown was calculated by this relative humidity and ideal gas equation. Okay, not basic, average problem. So you will see 3 or 4 problems like this in the first exam for 1 hour. So you need to practice as much as you can, okay? I'm telling you, Thermo 2 is not easy.
Figure by yourself.
This one? Yeah, here.